Now that we've analysed our insurance model under perfect information and void information, both being cases of symmetric information, where everybody knows the same thing, whether everybody knows everything or whether everybody knows nothing, the results were easy to derive and were very nice. So equilibrium existed and it was Pareto efficient. All of the consumers received full insurance at the actuarially fair price. Now it's time to consider asymmetric information and its, frankly, devastating effects in this model. So when we introduce asymmetric information now, what we mean is that consumers will know their own type, but the insurance firm has no way of distinguishing between the different types. As a result of this, in order to offer separating contracts in equilibrium, different contracts for the different types of individual, these contracts are going to have to be designed in a clever way using something called an incentive compatibility constraint, which is one of the most important ideas in modern economics, a central idea in mechanism design. Incentive compatibility was first expressed, I believe, by economics Nobel Prize winner Leonid Hurwitz, and the theory of mechanism design was fully developed by two more Nobel Prize winners, Eric Maskin and Roger Myerson. In this model, we're going to derive several results. The first important result will be that pooling equilibria, so under asymmetric information, offering everybody the same contract, simply cannot happen in equilibrium. So that's something we will prove first. This means that if there is an equilibrium, it has to be a separating equilibrium, which means each type, high risk and low risk, will need to be offered a different contract. And because there's asymmetric information, we're going to have to design those contracts in a clever way so that the individuals choose their own contract. We can't force them to choose their own contract because we can't identify which type is which. So that's where this idea of screening and incentive compatibility comes into play. It's a constraint, which means there's going to be a cost. There is going to be a welfare loss in under asymmetric information compared with the perfect information case. The final result, and the most devastating of all for economic theorists, is that when we have asymmetric information, if there's an equilibrium, it must be a separating equilibrium, but it might be that there is simply no equilibrium at all. This is what we will prove at the end of the lecture. Let's get started. Okay, so let's start our analysis of asymmetric information. So individuals, consumers know their own type, but firms cannot distinguish between different types. So our first result will be that in these circumstances, pooling equilibrium cannot occur. So if an equilibrium exists, it has to be a separating equilibrium. So why is this the case? Let's prove that pooling equilibrium does not exist under asymmetric information. So I've prepared a diagram. We have to get used to preparing lots of these diagrams with our contract space, with the good state level of consumption on the x-axis and the bad state level of consumption on the y-axis. This point here, labelled E, is the endowment, and this flatter straight line is the zero profit line selling to high risk types, and this steep line is the zero profit line if I'm selling contracts to low risk types. Now, if we're under a pooling equilibrium, so let's write pooling, a pooling contract it must be that I'm selling it to everybody. I'm selling one contract to everybody. So what would the condition for such a contract to earn zero profit look like? Well, we've seen this before. If I'm selling the contract to everybody, there would be a zero profit line something like this. Okay, and let's label this pi x equals 0. Okay, so type X was the type that doesn't know their type, or you could think of it as all types. So I'm selling to everybody. There is a, remember we said the probability of the bad state occurring for this type would be a beta proportion have probability PL of ending in the bad state, and a 1 minus beta proportion have a probability pH. Okay, so the slope of this line here would be 1 minus px over px. Okay, so if I'm selling one contract to all types, the first condition of an equilibrium is that it earns 0 expected profit. So it has to lie somewhere along this line. Okay, so let's just pick a point. We could pick any point we like. I'll pick it close to the 45-degree line just to make what follows a bit easier to see. So let's pick a contract here and call it C. Can this contract possibly be an equilibrium? Okay, and we want to prove that it cannot be an equilibrium. So why is this? Well, both types are going to be asked if they want contract C. Now remember, low risk types have steep indifference curves. So if I draw these steep indifference curve through C, okay, so this IL would be an indifference curve for a low risk type, and high risk types have flatter indifference curves tangent to the 0 profit line on the 45-degree line. So something like this. We need to make sure that we draw them so that they're always downward sloping, which is tricky. So that would be an indifference curve for a high risk type. Okay, so this is sometimes called the single crossing property. Essentially, these indifference curves will cross, and they'll only cross once at any point, like this contract here, C. Now, what do we notice about this? Well, it opens up this area here, which I'll shade because it's going to be interesting for us. Hopefully that comes up on the camera. So what in this shaded area, if I pick a contract here, let's call it C tilde, okay? C tilde. And if C is the contract being offered, suppose another firm comes along and offers the contract C tilde. Well, it's below the indifference curve for high-risk types that passes through C, okay? So we could note H types prefer contract C over C tilde. But what about the low-risk types? The low-risk types have these steeper indifference curves. C tilde is a riskier contract than C, but because they're low risk, it's better for them than C. So L types, the low-risk types, prefer C tilde. Okay, so that's the first step of the proof. If a pooling contract is offered, there will always be another contract such as C tilde with the property that if it is offered, it will essentially steal all of the best customers and none of the worst customers. Okay, it's going to take all of the low risk types away from C because low risk types prefer C tilde to C. And all of the high-risk types will keep buying contract C. They don't want contract C tilde. It's too risky for them. They know they're high risk. Okay? So the question now is C tilde profitable? Okay, we know that if C is an equilibrium contract, then there shouldn't be a contract that dominates it. So we've already got part of this domination here, that the low risk types like it better. So the question is, can C tilde make profit? Well, clearly in this diagram, I could just look at this and say, well, this is the 0 profit line for low risk types, and C tilde, I've drawn it below that 0 profit line. So if I'm only selling C tilde to low risk types, then the answer to this is yes. C tilde can make profit. Now, in the lecture notes, I did this a little bit more analytically, which is a little bit more convincing. I said, let C tilde be close, and I'll just to C, as in like a continuity argument. Let's take it closer and closer and closer to this contract C, but in a way that maintains that separation. Okay, well, what will happen then is that the profit from selling C tilde to low risk types will be approximately equal to the profit one would get from selling the original contract C only to low risk types. Okay, and this has to be better than the profit you would get from selling the contract C to everybody, because that includes the high risk types as well. And we know that that's zero. Okay, so this is kind of a more convincing argument that says the single crossing property here says that such a C tilde exists that will separate high risk and low risk types. And by taking this C tilde close to C, we can do it in a profitable way. And of course, if a pooling contract were indeed in equilibrium, it shouldn't be the case that we can find another contract that dominates it, a contract such as C tilde that some consumers want and that it can be sold profitably. The overall result is that any contract that is a pooling contract in this case of asymmetric information simply cannot be an equilibrium. If an equilibrium exists, we're going to need to use two contracts, one for the high risk types, one for the low risk types, and they must not equal each other in equilibrium. So now let's have a look at the case of a separating equilibrium under asymmetric information, assuming that it exists. So I've prepared a diagram here, in which I've placed the equilibrium contracts we derived under perfect information. Okay, so remember there were 4 equations, but 2 key properties was that the first property was that the expected value of these contracts, so the expected value of the contract C for type I when we're selling it to type I had to equal the expected value of that type's endowment, where I is equal to H and L. So there's two equations there. CH lied on the zero profit line, CL lied on the zero profit line for their respective types. And then the second condition was that they were the most preferred contracts that satisfied the zero profit condition. And we were able to separate the consumers under perfect information simply by assumption. We just imagined, well, all of the consumers, we know which types of consumers are which, we can identify them, and so we can tell high-risk types, you simply can't buy the low-risk contract. Now let's think about asymmetric information. So if these contracts were offered under asymmetric information, what would happen? Well, the low-risk types would look at CL and CH, okay? And of course, the low-risk types have no reason to want CH, okay? And indeed, there's no reason to prevent low-risk types from being CH. They're not going to pretend to be high-risk types, but even if they did, firms would only benefit from such a lie. And so we're going to quickly jump to the conclusion that contract CH isn't going to change. There's no reason for it to change. And so we could write the condition CHB equals CHG. Okay, so under asymmetric information, the high-risk types receive full insurance at the fair price. Now, let's think about how the high-risk types would look at these two contracts. Okay, well, if I'm offered a contract CH or CL and the firm has no idea what type I am, clearly if I'm high-risk type, I can get onto a much higher indifference curve by choosing CL. So high-risk types have an incentive the most important word in microeconomics. They have an incentive to lie about their true type. They're simply going to pretend to be low risk, and there is nothing the firm can do about it if it's offering CL. Okay? So technically, we would say that contract CL here is not incentive compatible. Okay, so let's cross it out. We're going to need a different contract, CL. So this condition, incentive compatibility. Okay, what do we require? What we require, now the second condition for an equilibrium was that high-risk types buy the high-risk contract or accept the high-risk contract. Okay, now they could, under asymmetric information, pretend to be low risk. So we're going to have to incentivize their honesty, in a sense. We're going to have to make it worth their while to choose CH over CL. Well, how do we do that? We're going to have a constraint that says the expected utility for a high-risk type, looking at their own contract CH, okay, has to be greater than or equal to the expected utility a high-risk type would get from choosing contract CL. Okay, so this is, remember, this just represents preferences. So it says if you're a high-risk type, you do not strictly prefer the low-risk contract to the contract that is offered to you. Okay, that is the key condition. It's an additional constraint, so it's imposing a cost. But this is the most important condition. This is what we call screening. So it's a self-separation. The individuals, the consumers in this economy will choose their own contracts because they have no reason to choose anybody else's, provided this condition is met. So what does this rule out? Well, we said we can't have any... We know that low-risk contracts have to lie along this zero profit line, but they can't lie they can't be above this indifference curve we've labeled IH. Okay? Sometimes I label this constraint ICH, the incentive compatibility constraint for the high-risk types. Essentially, it's saying CL cannot be anywhere here. It has to be in this region down here, so between C and where the indifference curve intersects this zero profit line. Okay, so all of these contracts, I know it's quite a small area, but all of these contracts between E and this point here, okay, so between E and this point here are incentive compatible. Okay, if we offer the low risk contracts here, they earn zero expected profit, and the high risk types are not going to pretend that they're low risk types. They're going to choose their own contract. Okay, so that's the key region. And then in equilibrium, what happens? Well, an equilibrium condition was that the individuals get the most preferred of all feasible contracts. And so in equilibrium, the constraint ICH binds. Okay, if you haven't heard this term before, it means we could have had a weak inequality here, a strict inequality, apologies, but binds means that in equilibrium, actually, this is an equation. Okay, so the expected utility a high-risk type gets from their contract has to be exactly equal to the expected utility a high-risk type would get from choosing the other contract. Okay, so that they will be indifferent between the two contracts, which is fine. We can then just assume that they get contract CH. They have no reason not to in that sense. Okay, so what does this mean graphically? It means that where this indifference curve intersects this zero profit line, i.e. this blob here, that is now the equilibrium contract CL under asymmetric information. Okay, so let's notice a few things about this. First of all, the high risk types are not being punished at all in this. Okay, so there's a notion of adverse selection here. We have asymmetric information. We kind of have a better type and a worse type, the high-risk types being the worse. And high-risk types get exactly the same outcome as they would under perfect information. They get CH. Okay, but to stop the high-risk types getting anything better, we have to make the low-risk contract worse. Okay, so the better types are the ones that are punished here. Notice that low-risk types are on. Then the diagram's getting a bit compact, a bit full, but you could draw an indifference curve for a low-risk type through this point, and notice that there is a big drop in utility going from perfect information to asymmetric information. And so that is the cost of asymmetric information. It's borne entirely by the low-risk types because the high-risk types happen to exist. Okay, so there it is. If an equilibrium exists, it's characterized by these equations. Both contracts earn zero expected profit. The high-risk contract is risk-free, and that's a third equation. And the fourth equation is that an incentive compatibility constraint binds. So now that we've analyzed the case of asymmetric information under the assumption that an equilibrium exists, let's summarize our results. If the equilibrium exists, it must look like this. It is characterized by three conditions. The first is that both contracts must earn zero expected profit. So really that's two equations. So our three conditions generate four equations, which is what we want because each contract has two dimensions. So we're trying to find four things. These four equations should do the job. So both contracts earn zero expected profit. The low-risk contract lies somewhere along that blue line, pi L equals 0, and the high-risk contract lies somewhere along that red line, pi H equals 0. We know that the high-risk consumer is offered a full insurance contract. That is the most preferred of the zero profit contracts for high-risk types, and there's no reason to give them anything else. And so the high-risk types receive exactly the same contract as before. Now, if we were to offer the low-risk contract on the 45-degree line along that blue line as well, as we did under perfect information, of course, all of the high-risk types would simply lie about their type, pretend to be low risk, and take the better contract. And so we need to make sure that the contract for low-risk types lies on or below the indifference curve labeled IH. This was the incentive compatibility constraint. So below the red indifference curve IH and somewhere along that blue zero profit line are the incentive compatible zero profit contracts. And because it's an equilibrium, consumers are offered the most preferred of these feasible contracts. And so the incentive compatibility constraint binds. It holds with equality. The high-risk type must be precisely indifferent between their contract and the low-risk contract. Of course, if they're indifferent, they could choose either, but they have no reason not to choose contract CH, which is all that we require for an equilibrium. Notice two things. The first is that high-risk types essentially are the worst types in this model. They are the undesirable types, and yet they are not punished in this case compared to the perfect information case. It is the low-risk types who are punished. So there's a sense of adverse selection occurring here. All of the cost of asymmetric information is being borne by the low-risk types who cannot be offered anything as good as the contract they would get under perfect information. Okay, so this is not a Pareto efficient solution. There would be a way of taking a group in this model, namely the low-risk types, and making them better off by offering them a full insurance contract. But we simply can't do that because when there is asymmetric information, we add this constraint of incentive compatibility. And of course, an additional constraint means an additional cost. The contract simply can't be as good as the perfect information case. Now that we know what the competitive equilibrium contracts under asymmetric information must look like if an equilibrium exists, let's discuss why an equilibrium may not exist at all. Now remember, the only change we're making compared to our perfect model where everything worked out nicely, everybody got fully insured, and the equilibrium was Pareto efficient, the only change we're making is that there is asymmetric information. So we already know that if the equilibrium exists, it must involve costs. So the low-risk contract is worse than it would be under perfect information. This is incentive compatibility constraint, induces a cost, which is the cost of asymmetric information here. Now, let's look at this contract CL a little more. If I draw a low-risk types indifference curve through this point, so here I've drawn a curve labeled IL, then anything that is above this curve would be preferred by the low-risk types. So have a look at this contract here I've labeled C tilde. Now C tilde is it's clearly better than CH. If you're high risk, it would be on a higher red indifference curve. And also if you're low risk, C tilde would be on a higher indifference curve. So everybody likes C tilde better than our candidate for an equilibrium. So here is the important question. Can a contract such as C tilde make positive profit? If it could, then a firm will certainly offer this contract and it will dominate the separating candidate for an equilibrium. So let's analyze this question. Can it make positive profit? Well, if beta is very low, so there is a very low proportion of low risk types, a very high proportion of high risk types in this economy, then the zero profit line for pooling contracts, contracts that everybody buys, would be this purple line, pi x equals 0, under the assumption that beta is close to 0. So it's closer to the pi h equals 0 line than it is to the pi l equals 0 line. Well, in this case, clearly C tilde would be on a higher ISO cost than the zero profit line. And so it would necessarily lose money for the firm. It would incur a negative profit, in which case the candidate C tilde, which is better for the consumers, no firm is going to offer this. And so in this case, the separating contracts CH-CL do indeed constitute a competitive equilibrium. Now suppose we had a case where beta is high, close to 1. There are a very small number of high-risk consumers in this economy and a very large number of low-risk consumers. Well, if that is the case, then this purple pi x equals 0 line, when beta is close to 1, is much closer to the low-risk zero profit line. Okay, and I've drawn it quite steep here, and clearly in this case C tilde would be on a lower ISO cost than the zero profit line, which makes it a contract that would earn strictly positive profits. So what do we have? Well, we have the only candidate for an equilibrium, CHCL, is dominated by a pooling contract, C tilde. It earns positive profits, and both types of consumers like it better than the separating contracts. Okay? But what do we know about pooling contracts? Pooling contracts are inherently unstable. They can never be equilibrium. A pooling contract can never be an equilibrium contract. We've already proved this. So we have that no pooling contract can be an equilibrium contract because firms would undercut each other in the kind of more sophisticated way that we showed before. So C tilde cannot be an equilibrium contract, but it is better in every way than the only candidate for an equilibrium, which is the separating contracts. And so in this case, there is simply no equilibrium at all, simply because we introduced asymmetric information into this model, and because the proportion of low-risk types was very high, this model has no equilibrium. So that completes our study of the Rothschild-Stiglitz insurance model for now. We'll come back to it a little in the next lecture. Note that the major result, the most surprising result, the fact that an equilibrium might not exist in this model, was purely a consequence of asymmetric information. Otherwise, the model worked absolutely beautifully. As soon as we had asymmetric information, the results completely changed. So if we go back to that initial quote from Rothschild and Stiglitz, that the previous belief that the study of information may complicate without informing, of course we now see this is false. Including or taking asymmetric information into an account in a serious way didn't just make our results more difficult, they completely changed the qualitative nature of the results. Equilibrium is no longer efficient when it exists. It involves large agency costs or costs of asymmetric information or incentive compatibility. It's a constraint, it's a cost. And also the possibility that equilibrium simply might not exist. This is a major change in the results. In the next lecture, we're going to study something called the value of information. So how can we place a value on a source of information? And we'll prove some basic results immediately that in single-person decision-making, information can never have negative value. Okay, so you would never pay not to have information if you're a single person decision maker. Then we will look at examples that completely reverse this result from the world of game theory and also in markets. So when there are more people involved in the problem, then it is possible that including more information in a market or in a game can actually lead to worse results. We'll give some examples next time. I look forward to seeing you. In the meantime, take care.